If you've ever wondered why it's harder to spin a door near the hinge than at the handle, or why pulling your arms in makes you spin faster, then you've already understood the idea behind rotational inertia. In this video, we're going to break down rotational inertia, also called moment of inertia, which is one of the most important ideas in physics and rotational motion. By the end of this video, you'll know the formulas, the intuition, and how to solve the hardest exam-style problems involving moment of inertia. So, first off, let's start off with the preliminary knowledge of what is rotational inertia. Rotational inertia is the resistance. It measures this resistance of an object to changes in rotational motion. So here, M is the mass element, and R is the distance from the axis of rotation. And essentially, mass further from the axis increases the rotational inertia dramatically. See, as you can see, it depends on the mass distribution, so farther from the axis means a larger I, and resistance to rotational acceleration, which is the analog of mass, is angular. Larger I means harder to start or stop rotation, and the distribution of mass matters more than the total mass, which is very important. So let's compare quickly linear versus rotational. Some quick things. Let's reiterate. So we know that linear you have mass m, right? But in rotational you have moment of inertia again, which is just I. Here you have force F, and here you have torque tau. And then you have acceleration A, and then you have angular acceleration alpha. So moment of inertia plays the same role that mass plays in translation. So some common moments of inertia that you have to memorize are down here. So as you can see here, solid shapes always have inertia that is less than mr squared because the mass is closer to the center. And a rod about the center has inertia is lesser than the rod about the center because the r is smaller. Start off with a solid disk, aka the solid cylinder. So the formula is going to be I is equal to either m divided by 2 times r1 squared plus r2 squared, or more simply, I is equal to 1/2 of mr squared. So the axis is going to be at the center, and the moment of inertia, again, is just 1/2 mr squared. But let's actually add one more down here. Let's start off with point mass. A point mass. The distance, the axis of rotation is going to be distance r, and this is basically your base case. The moment of inertia is just I equals mr squared. So let's start off with let's continue on with a ring or a hollow cylinder hoop. So that's going to be I is equal to mr squared. Now let's talk about a thin rod, which is this. I is going to equal to 1/12 mr squared. Let's go one at a time. And let's talk about a thin rod at its end. A thin rod at its end. A thin rod at its end is going to be 1/3 ml squared. And let's talk about a solid disc or a cylinder about its center. So a solid disc or a cylinder around its center is just 1/2 mr squared up here again. And let's talk about a solid sphere. A solid sphere is going to be I is equal to 2/5 mr squared, with the axis being at the center. And again, the hoop ring is going to be I is equal to mr squared. So now let's talk about the parallel axis theorem. The parallel axis theorem is here, and d is the distance between the new axis and the center of mass. So an idea that you have to understand is that rotational inertia depends both on mass and how the mass is distributed. So rotational inertia, it depends on the mass and how mass how the mass is distributed. That's important. So again, this idea explains why a hollow ring rolls slower than a solid disk. So let's write these down. A hollow ring rolls slower than a solid disk. Because again, this relates back to those formulas that we were looking at earlier. Let's actually move these over a bit. And also this explains why figure skaters famously spin faster when arms are inward. And this is why axis choice matters more than object shape alone. So essentially, where the reference as to where you create your axis is more important than whatever shape you have always. So now let's start off with problem 1. A solid disk of mass m and radius r rotates about its center. The axis is moved to the edge of the disk. By what factor does the moment of inertia increase? So let's start by drawing out both of the scenarios. So before and after the change. So we have a solid disk. So the disk is gonna be like this. And let's say, okay, so the disk is going to be like this. And then we change the axis of rotation. So originally it is rotating around its center, right? See the disk rotating around its center, but then the axis moves to the edge of the disk. So you want to find the difference in the moment of inertia. So we know that around its center, it's going to be equal to I center of mass is going to equal to 1 over 2 mr squared. But then the distance to the new axis, that's going to be the distance. That's going to be, we're just going to set that equal to r. And now we have to apply the parallel axis theorem. And applying this, we know we can write that I is equal to the I of center of mass plus md squared. So I is just going to equal to 1/2 of mr squared plus mr squared. And together, this is going to equal to 3 over 2 mr squared. So now, what we want to do is find the factor increase. And how do you do that? You just basically take the ratio of both of them, and then that's how you find the ratio. That's the factor. So the I new divided by the I old. And we know that the new is 3 over 2 mr squared, which we just calculated, and the old was 1/2 mr squared. And then now we can cancel out those 2's, that, and then all that we're left with is just 3. So it increases by a factor of 3, actually. Now, let's continue. So what does this mean? It means that moving the axis outward greatly increases rotational inertia. So now let's continue with the second example. A solid sphere and a hoop have the same mass and radius. Both rotate about their central axes. Which is the larger rotational inertia? So let's start off by writing and drawing the solid sphere. So we have a solid sphere. So it's going to be, just imagine a circle. And then the sphere is rotated about its central axis. And then let's say we have the hoop. The hoop is going to be like this. Hoop like this. Okay. Around the center axis. So the solid sphere is going to be I is equal to 2 over 5 mr squared. And then the hoop is going to be I is equal to mr squared. And now we compare. So we know that this is greater. So therefore, hoop has greater rotational inertia because this is actually r squared. So this is being multiplied by 2 over 5. So it's going to be 2 over 5 less than this. So obviously the hoop has a greater rotational inertia. So mass further from the axis dominates the rotational axis. So the mass farther from the axis dominates the rotational inertia. Let's write that. Mass farther Now let's continue with our third example. 3 point masses are located on a rod, m at distance r, 2m at distance 2r, and m at distance 3r. Find the total moment of inertia about the center of mass. So we can use the definition that inertia is equal to the sum of mr squared. So I is going to equal to mr squared plus 2m times 2r squared plus m times 3r squared. Simplifying this algebra, we get mr squared plus c2 times 2, and then that's going to be 4 times 2, that's going to be 8 mr squared, and then this is going to be 3 squared, that's going to be 9 mr squared. The inertia is going to be 18 mr squared. Therefore, doubling distance increases contribution by factor 4. So again, remember that rotational inertia, it depends on mass distribution. The distance and also the distance from the axis matters. Distance from axis matters more than mass. So it can be really big or really small, but what's really important is how far away it is from the center. Axis choice is critical. Also memorize all the standard I formulas and also use the parallel axis theorem correctly. All right, thanks for watching.